Picture a quiet test range in West Palm Beach. Humid air. A handful of engineers staring at telemetry screens. A pilot tightening his harness inside a machine that looks familiar enough to be a helicopter, yet carries the kind of confidence only seen in experimental prototypes. Everyone expects the usual signs of rotary flight as it lifts off. The thumping, the shake, the sense that the aircraft is working against the sky more than with it. But the moment the X-2 leaves the ground, something feels wrong in the best possible way. No wobble, no fight, just a smooth climb that makes the veteran pilots watching shift in their seats. Then the acceleration starts. Clean. Effortless. Almost suspicious. 150 miles per hour, then 200. 230. The numbers jump so fast the room goes quiet. Helicopters aren't supposed to move like this. They aren't supposed to feel like this. And yet the X-2 keeps pushing until it feels less like a rotorcraft and more like a secret someone forgot to classify. And here's where the story gets even stranger. This video uncovers how Sikorsky built a helicopter that outran its own rules, why the technology worked, and why the world hesitated. Before we begin, hit subscribe so you don't miss stories like this. For almost a century, helicopter engineers lived with a simple truth. A helicopter can lift, hover, pivot, slip into tight places, rescue people from spots where fixed wings wouldn't dare. But it can't outrun anything. Not jets, not turboprops, sometimes not even a car on a good highway. Speed was the tax you paid for vertical flight. The reason sat right above every pilot's head. A rotor system that behaves beautifully at low speed turns into a physics problem as soon as you push the throttle forward. On one side of the helicopter, the advancing blade bites the air so fast that its tips flirt with transonic shockwaves. On the opposite side, the retreating blade slows down so much it begins to lose lift. That imbalance twists the aircraft, strains the controls, and creates the kind of vibration that feels like the airframe is trying to shake itself apart. Then there's drag. A classic helicopter drags its rotor through the air like a giant spinning brake. Push hard enough, and the rotor simply refuses to give you more. It stalls, it shakes, and eventually it punishes every extra knot you try to squeeze out of it. By the mid-2000s, the speed ceiling felt final. The standing record from the 1980s sat near 216 knots, and attempts to push beyond it turned helicopters into unstable, fuel-guzzling testbeds that pilots endured rather than enjoyed. That was the world Sikorsky walked into. A world that believed helicopters had reached their natural limit. And yet, inside one Connecticut design office, a small team looked at that limit and didn't see a wall. They saw an opening. Sikorsky had tried the fast helicopter experiment once before. The S-69 in the 1970s hinted at wild potential, but came with a price. Violent vibration, terrifying fuel burn, a workload that demanded 3 hands and nerves of steel. The idea was right, the execution wasn't ready. Fast forward 30 years. Warfare has stretched across deserts, mountains, and sprawling battlefields. The Army needs aircraft that can move far, arrive fast, and survive. Traditional helicopters can't close the distance quickly enough. Tilt rotors help, but they come with their own compromises. Somewhere in the mix, the old question rises again. Is there a way to make a helicopter fly twice as fast without turning the cockpit into a punishment chamber? Inside Sikorsky, a small, stubborn group thinks the answer is yes. They want another shot, another experiment. But this time, they refuse to brute force anything. They want elegance, balance. A machine that breaks records without threatening pilots. The company approves a quiet project. No flashy announcements, no promises to the Pentagon. Just a mission. Build something that proves fast helicopters aren't fantasy. They're simply misunderstood. The idea becomes the X-2. A demonstrator with no weapons, no armor, no pressure to enter service. Just one goal. Break the speed wall in a way that feels repeatable, predictable, viable. This isn't a moonshot. It's a calculated gamble that if Sikorsky can show smooth, stable, controllable speed, the military will finally pay attention. But to break a rule locked into aviation for decades, you can't tweak the old formula. You have to rewrite it entirely. At first glance, the X-2 doesn't look radical. No dramatic wings, no futuristic silhouette. But underneath that clean frame sits a design so different that engineers still smile when they explain it. The magic starts with the coaxial rotors. Two rigid rotors stacked on the same axis, spinning in opposite directions. No tail rotor needed, no torque to fight. And most importantly, no retreating blades starving for lift on one side. Each rotor carries part of the load, balancing the disc and letting the helicopter slip into speeds that single rotor designs can't tolerate. Then comes the trick in the back, a six-bladed pusher prop that kicks in once the X-2 accelerates. Traditional helicopters lose efficiency as drag builds. The X-2 removes that burden by offloading forward thrust to the prop. The rotors can slow slightly, reducing stress and vibration, while the prop does the sprinting. Fly-by-wire smooths out the chaos. Composite blades cut weight and handle stress that older materials would have hated. The whole system moves with a coordination that feels closer to a digital orchestra than a helicopter. Yes, it's complex. The gearbox alone looks like something an engineer would sketch on a napkin at 2 a.m. and then regret. But complexity doesn't mean fragility. It means precision. It means control. And it means the X-2 can sprint where other helicopters stumble. Together, these choices attack every problem that kept helicopters slow. And when all of it works in harmony, the air behaves differently, the machine behaves differently. And the moment Sikorsky put that theory into the sky, the numbers proved the point fast. Very fast. If stories about machines that rewrite their own rulebooks keep you hooked, hit subscribe. I've got more aviation secrets, more wild prototypes, and more forgotten breakthroughs coming your way. The first flight in 2008 wasn't meant to set records. It was a gentle hop, a systems check, a moment for pilots to feel out the controls. The X-2 lifted, hovered, turned, and settled like it had nothing to prove. Engineers nodded, pilots smiled. The machine behaved better than expected. That alone felt like a win. Then the team started pushing it. One flight reached 150 knots. The cabin stayed calm. No violent shake, no angry rotor thump. Later tests hit 180, then 200, with the same uncanny smoothness. The pilots joked that it felt like cheating, like the air forgot to punish them. The milestone came in September 2010. Sikorsky aimed for a clean, verified run to eclipse the decades-old record. The X-2 leveled out, the prop engaged, and the helicopter slipped past 240 knots with a confidence that made the telemetry team fall silent. Then it touched 250 knots in level flight. A shallow dive nudged it even higher. The record wasn't just broken, it was shattered in a way that left no argument. The X-2 wasn't a stunt or a fluke. It was a helicopter flying at speeds only tiltrotors and fixed wings had any business reaching. But the most important detail wasn't the top number, it was the feel. The X-2 was stable, predictable. A pilot could fight in this machine. They could escort, scout, insert, extract. It didn't behave like an experiment. It behaved like a future. But once the speed numbers became undeniable, Sikorsky discovered something tougher than physics. Convincing the military that the future was actually worth buying. The record proved the physics. What came next would test something harder. Trust. Inside the Pentagon, the reaction to the X-2's numbers was a strange mix of excitement and hesitation. The Army had asked for speed for years. Long-range missions, rapid insertion, fast-armed scouts. The X-2 delivered all of that on a silver plate. But military planners don't just chase performance, they chase predictability. A standard helicopter has decades of operational history behind it. Thousands of flight hours. Training pipelines already built. A coaxial compound helicopter is a leap into the unknown. 2 rotors to maintain. A pusher prop to protect. A gearbox that looks like aerospace jewelry. And a flight control system that depends heavily on digital smoothing. The Army wasn't doubting the numbers. They were doubting the ecosystem around them. How would it handle dust, mud, battle damage, night operations, logistics stretched across overseas bases? No one knew, and when billions are on the line, no one knows is the enemy. Budget timing made it worse. The Armed Aerial Scout program was already wobbling. Requirements shifted. Priorities changed. The service wasn't sure if it even wanted a new scout aircraft anymore, which meant the X-2 wasn't fighting another helicopter. It was fighting indecision. Sikorsky kept pointing at the data. Smooth flights, low vibration, actual stability at 250 knots. But military culture moves slower than prototypes, and the X-2 was moving faster than anything the system was ready to support. So Sikorsky changed the pitch. If the Army wanted proof, they'd build it again. This time bigger, stronger, and undeniably operational. Sikorsky didn't walk away after the X-2 retired in 2011. They doubled down. If the Pentagon needed confidence, they'd scale the technology into machines meant for actual missions. The first was the S-97 Raider, a sleek weapon-ready scout and light attack helicopter designed to cruise above 220 knots and maneuver in ways no traditional airframe could match. It kept the coaxial rotors. It kept the pusher prop. It kept the fly-by-wire heartbeat that made the X-2 so calm at high speed. Raider wasn't just fast. It could turn inside its own radius at speeds that would force a conventional helicopter to back off. It could stay low, hug terrain, and accelerate instantly when it needed to. The Army took notice. Demonstration flights showed a real military machine, not a lab experiment. Then came the next step. SB-1 Defiant, a scaled-up transport and assault concept that brought X-2 technology to Black Hawk territory. Twin engines, room for a squad, the ability to haul troops faster and reach landing zones before defenders could react. If Raider proved the agility, Defiant proved the reach. The message was clear. X-2 wasn't a one-time stunt. It was the blueprint for an entire family of next-generation rotorcraft ready to plug into the Army's future vertical lift vision. Suddenly, the technology didn't look risky. It looked inevitable. But even with real prototypes, real missions, and real performance, one question still haunted the story. If this works so well, why isn't every helicopter built this way? On paper, the X-2 solves nearly every classic helicopter limitation. In practice, it forces the industry to rethink everything at once. Speed is the reward. Complexity is the price. Start with the mechanics. A coaxial, rigid rotor system demands extreme precision. The hubs must endure massive loads at high speed. The gearbox has to handle inputs no conventional helicopter ever experiences. Maintenance crews need new tools, new training, and a comfort level with systems that behave more like fighter jet components than utility helicopter parts. Cost matters too. Traditional helicopters have global supply chains, predictable life cycles, and familiar support needs. The X-2 family asks militaries to upgrade infrastructure. Army planners have to justify that leap while managing budgets already stretched by wars, modernization programs, and competing aircraft proposals. Then there's timing. When the X-2 first proved itself, the Armed Aerial Scout program collapsed. Years later, future vertical lift became the big priority, and tilt rotors entered the competition with long-range efficiency that matched different mission profiles. The X-2 wasn't beaten by physics. It was slowed by bureaucracy, timing, and the inertia of existing fleets. Noise and infrared signature also raised questions. A pusher prop and coaxial rotors create new acoustic footprints that commanders have to plan around. Not fatal issues, but issues that require doctrine changes. So the reason isn't doubt, it's inertia. The X-2 demands a shift in operational thinking, logistical networks, and procurement comfort levels. It's not that the technology is too advanced, it's that the system built around helicopters hasn't fully caught up. Yet even with these obstacles, one thing is certain. The X-2 didn't fade into history. It quietly shaped what may become the fastest generation of rotorcraft ever built. So the X-2 didn't rewrite aviation overnight. But it cracked a barrier everyone thought was unbreakable and proved that helicopters could outrun the limits written for them. Its DNA lives on in Raider, in Defiant, and in every high-speed concept rising behind closed doors. Because sometimes the future doesn't arrive with fanfare. It starts quietly, with one machine daring the sky to keep up.